Hi guys. Today I'll be talking about chapter 14.7, part 2, and it details the use of triple integrals and other coordinates. So not rectangular or spherical or cylindrical, but we're talking about spherical coordinates today because Edgar covered rectangular and cylindrical coordinates. And so in order to truly understand how to use spherical coordinates, we have to look at what how to convert rectangular into spherical. So these three equations right here will be the most important when converting equations into spherical coordinates. So from Cartesian to spherical. And I also forgot this rho squared equals x squared plus y squared plus z squared will also be very important when deciding how to use spherical coordinates. So these will be used to convert, and the reason why we use spherical coordinates is so that we could help make triple integrals that might be more difficult to do in rectangular to make it more simpler and to make it a lot easier to solve. So the general equation would be so from rectangular into cylindrical into spherical. I mean, my bad. Using this this what do you call this? Transcription. So you would use instead of x, you would substitute for rho sine phi cosine theta, and for y, rho sine phi sine theta, and for z, rho cosine phi. And also, it would use you would also have to add in rho squared sine phi when you're doing these conversions. So this right here is very important. You must not forget it. And so we would change it from dv, so dx, dy, dz into d rho, d theta, and d phi. So this is how it would look like. So if you're looking at a point that is this far away, you would look at this the xy plane, the angle between in the xy plane would be theta as usual, and the angle between the z-axis and the xy plane would be this phi value right here. So it would change if the point is going up or down, and also the rho value would be the distance from the origin to the point. So that line right there would be the rho. And this is how the conversion would look like in a traditional sense. Okay, so moving on, we're going to tackle one example, an example of how to find volume in spherical coordinates. And this is another key point of using spherical coordinates. So we would find, so the question, an example question would be to find the volume of an unknown solid region bounded by a surface of another region. So in this case, it would be a cone with the equation z squared equals x squared plus y. That would be the cone. And the sphere x squared plus y squared plus z squared equals 9. So this would be a fairly simple question. So the first step would be, in my opinion, to visualize what you're trying to solve. So let's do the easy one first, the sphere. So we know that x squared, this would be a spherical equation, and this would be technically rho. This would be x squared plus y squared plus z squared equals rho squared. So rho squared equals 9, and rho would equal 3. So that would be the distance from any point to the origin. So let's see, it would look like this for the sphere. You draw these 3 points, and then let's draw. Oh. It would look somewhat like that, like a sphere. Pretend that's a sphere. And then For the cone, it would be, so you could also visualize this quite easily. Some questions might be a little more difficult to visualize. But so the x squared and y squared, so the xy plane would diverge as you increase in height. So towards the z-axis. So it would be, let's say if z would equal to 1, then x squared plus y squared. So it would just like, I'm not gonna like plug in all the points, but it would look something like a cone kind of thing right here. And you're trying to find the region bounded between it, so it would be the top of the sphere and inside the cone. So it would be like something like that. It's hard to visualize. I apologize. So in order to tackle this question, first you would need to find ways to find how to solve and convert this equation from these equations from rectangular to spherical. And then so first you would you would use the equation that you already know. So rho squared equals x squared plus y squared plus z squared. So use that, and you see how it conforms to that conversion already. So you would use, obviously it would be rho, so 9 equals x squared plus y squared plus z squared from that. And you can see that rho squared equals 9, rho equals 3. And then for the z squared equals, for the cone equation, you could see that, so I'll just write it down, like repeat it to make it easier to visualize. And then x squared plus y squared plus z squared equals 9. So you see how this right here, x squared plus y squared, could also shift inwards towards that. So it could substitute this equation right here. That would substitute. So you could get z squared. So you could get z squared plus z squared equals 9. So that would be 2z squared. Alright, this is part 3 of the extra credit project. And I'm running out of space on my phone, so I gotta make it quick. So basically, we're on this part, so we found the total triple integral. So we just need to evaluate it now, which shouldn't be too hard. It's a pretty simple integral. So obviously that would be 2 pi 3 0. That would be sine phi. So it would come out to 9 sine phi d theta. And then we already know our previous. I have to rush through it because I'm going over the time, and I'm going over my phone limit. Okay, so 9 2 pi, and then just copy it down. That'll turn out to be pi over 4, so sine cosine phi, and then evaluated by pi over 4. So it'd be negative cosine phi because it's an integral. So that would be negative cosine phi. So it would be negative cosine phi evaluated from pi over 4 to 0, and then final d theta, and then that would result in, so 2 pi, so negative cosine pi over 4, cosine pi over 4 is 1. Negative cosine pi over 4 is right 2. Okay. To be 1 minus rad 2 over 2. I'm just rushing through it. 18 pi. So that would just result in just a theta right here. So it'll just be multiplied by 2 pi. So 9 by 1 minus rad 2 over 2. That would be the answer. And then you could simplify it to 9 pi 2 minus rad 2. That would be the simplification, and that would be the volume between the solid region. And that's all that I could